All right, so this is a recorded lecture for E351. We'll finish some parts of the power electronics section. Right, so last time we stopped by diodes. Right, so solid state diode is a p-n junction, allows the current to flow through one way. And if you look at solid state diode, basically the VI characteristic is that the diode turns on at about zero point 0.7 volts and then sort of block current flow going the other way. And this is a good characteristic, allows one-way power flow. But the drawback, this is no control, right? So there's really not a switching action going on. Whether the diode on or off, just depending on whether the voltage is applied, whether we apply for a voltage. So after a diode, a transistor is basically something where you can actually switch, right? So there's two types of transistors. One is called bipolar junction transistor. So this is, you can think of diode p-n junction. This transistor is a NPN. So there are three parts. And then one end of the transistor is called a collector. The other is called emitter. And then on this side this is called the base of the transistor. So in circuit diagrams, we'll draw this transistor this way. And really what we think about this transistor, this is a current control device. So the control is the base current turns the transistor on or off. Right? So depending on how much current is being applied to the base, then this transistor, either we can have current flow between C to E, or there's no current flow between C to E. So there's two cases. One, if we push enough current at the base, then there is some current flow between C to E, or if there's no current to the base, then this acts like an open, right? So in this case, this is a closed switch. In this case, this will act like a open switch. Now, bipolar transistors are fairly big devices, right? So, they're very robust, they're very big, and they can take a lot of power and current. So the characteristic of a bipolar transistor is, again, if you look at, is this just is a current control switch without going into too much details. So the advantage of bipolar transistor is that this is pretty reliable. It's pretty reliable, and it's sort of very robust. The dis the disadvantage is that the losses can be very high. The reason we have high loss is you're putting current. So we're putting current into this device. And then there's sort of some I square R loss that you can't really get rid of, right? So there will be some I square R loss. It's hard to eliminate this I square loss. And also you may need sort of fairly large base current to actually close a switch. So as an alternative, there's another type of transistor. This is the MOSFET transistor, and this is certainly sort of more commonly used transistors. So a MOSFET, instead of being a current control switch, this will be a voltage control switch. Right, so we basically have a gate voltage, and depending on what this voltage is, right? So we'll apply a voltage to the gate, And this voltage will control whether this switch is open or closed. And the benefit of this is there is not necessarily a loss, right? Or there is a much smaller loss associated with this voltage control device than a current control device. Okay, so this is smaller loss. It's sort of easier to drive voltage, right? So again, because the way that MOSFET works is this is actually insulated. So even if we apply a voltage, there is not no current flow. So therefore you don't have to have a gate driver that has power coming out of it. Whereas if you have bipolar transistor, because you're driving this using a current at the base, then there's some power, right? So your sort of driver, the control circuit needs to apply some power. Whereas for MOSFET, sorry, you just we can do it with a digital control circuit. So in the past, MOSFET were not as robust as bipolar, but nowadays I think most power electronics today use MOSFET devices, right? So and these can sort of switch at very high frequencies. Right, so looking at tens of megahertz, these can switch fairly fast. So in EE452, you'll learn a lot more about different kind of switches. So for this class here, for us, basically both MOSFET and bipolar junction are just again simulating ideal switches for us, right? So we wouldn't worry too much about the how the switch is made. We basically assume either transistor we're using just gives us a control switch. So that's the assumption we're making in this class. Okay, and the sort of then you can combine these. You can have you can combine a insulated gate with a bipolar transistor, right? So you can there's sort of many other devices we can do. Okay, and a lot of this depends really on the power level that we talk about, right? So for something that works in 5 to 10 watts may not work in 5 to 10 megawatt, right? So it really depends on the application. And for this class, sort of an important device that you may not see at other places is this thing so-called thyristor. So this is the silicon control rectifier. And with the way we think about this is basically a control diode. Okay. So when we had a diode, basically the diode just turned on at 0.7 volts, right? So it allowed a single direction of current flow and turn on when the forward voltage is 0.7 volts. Thyristor we are now think of is can we control when the diode turns on? Okay, so the idea is so we draw this basically as a diode with a gate. Right, so then the idea is if we apply some current pulse to this gate, then this device will start to conduct. Okay, so the idea is if you look at the current, we'll look at the current into the gate. And then so this is time t. So let's say at the beginning we have zero current. So here the basically this is off, right? So this is not conducting. And then let's say at some time we apply a narrow pulse of current. And then afterwards this could still this current still current returns to zero. But after applying this sort of pulse of current, after from this time until afterwards, this is off. Okay, so this is saying that I want to turn this diode on, and we do this by applying some sort of pulse of current. Okay? So we don't need continuous current like in the bipolar junction transistor. Here we can achieve this just by using a pulse of current. Of course, this is a less finer controlled action, right? So we're not really switching it back and forth. We're just switching it from off to on once. Right, and the way sort of we draw this is, we can draw the VI characteristic of this. So this is boy I, and then basically, so this is off for this part, and then let's say that we apply some current pulse here, and then this becomes a sort of conductor. So this becomes a conductor, and so it can have a sort of much larger forward bias region than the diode, right? So this is the reverse bias region. This is the forward bias. Right, and the idea is instead of just a zero point 0.7 volts for a diode, here we can sort of control however large this voltage is by decided by when we decide to apply current to this. Okay, so again, the closing of a CR, this is sort of close. This it goes from open to closed. This is by applying a IG. So our gate driver here, again, instead of continuous current, just apply sort of a short pulse of current, and then this turns from open switch to a closed switch. Okay. To open this, basically, this is not so. Unlike an actual transistor where you can, open and close the switch, here to open the switch is basically just the switch opens when the current is too small. So idea is this is opens the current from A to K. So this current is too small. Okay. So if this current is too small, for example, it's close to zero, then this thing opens. Okay, so let's call this IA. So let's say again, this doesn't, so at this time, the gate driving pulse, or IG, is already zero. So really, once this is on, really what we're looking at is there's some threshold voltage, IH. And if IA is less than IH, then then the SCR opens. So it was a closed switch, right? And we're pushing some current through this. And then if IA is less than IH, okay, so this switch you can think of sort of opens on its own if there's not enough current. Okay. So to apply this, or to open this, we apply some forward bias voltage. We apply a current pulse to the gate. And to open it, this thing just, when the current drops too low, and this will stay open until when we apply the next gate current pulse. So they're sort of fairly easy to operate. And the benefit of thyristors is this can take much higher current and voltage ratings than transistors. Okay. And because, again, it's a much simpler device, this is sort of much cheaper. This is just sort of can be triggered by a single pulse. So it doesn't take that much, doesn't take that much to trigger it. And this is This is returns. This is opens if current drops to 0. And this is called a natural commutation. So this is just a fancy way of saying that the sort of the device will open if you're not pushing current, right? So we don't have a sort of you're not right. So this is sort of the device is not staying on if there's no current being applied. There's no current going through it, right? So often in circuit design, we try to design a commutation circuit, but in this case, this comes for free. It comes from how we make the device. So the disadvantage is again the we have right. So the disadvantage is well to open this we need current to drop relatively close to 0. So turning it off or opening it when the current is not that close to 0 is actually not trivial. Right? Well, compare with a transistor, that's actually a switch, right? We can open the switch even when some current wants to go through it. But for thyristor, that's really hard to do, right? So, this was once it turned on, the switch closes, will stay close as long as there's some current that wants to go through it. Right? So if we, summarize basically all these devices, then we have sort of non-controllable. This be a diode, right? So the simplest thing to make, but not that controllable. So this is then we have somewhat controllable. This is SCR, right? Or the thyristor. And then we have sort of fully controllable devices. That's just the either the bipolar junction or the MOSFET. And these things sort of the cost goes as you would imagine. The sort of the simplest device, diodes is the cheapest to make, and and also and the transistors are the more expensive ones. And also voltage current rating is sort of the simpler the device, the easier it is to make them higher rating. Okay, so which one of these we use will depend on the application that we have. Okay. And the next we'll look at so we'll look at actually some circuits. We'll look at AC to DC converters, or these are called rectifier circuits. So there's a sort of the simplest rectifier circuit is basically just a the AC circuit with a diode in it. Okay, so let's say we have some source and we want to look at the voltage, and this is called V of t, right? We want to understand how V of t relates to V of s. So again, for us, we can ignore the turn on voltage of a diode. The voltage is high enough that this zero point 0.7 volts wouldn't matter. And if we have a source like this, if you look at the voltage as a load, then just the positive part passes through. Right? Depending on whether the diode is forward biased or reverse biased. So this is about as simple as we can make it. And it's slightly more fancy, right? So if you look at this circuit, basically half the wave gets through, right? So this is called half-wave rectifier. The controlled half-wave rectifier is instead of diode, we use SCR. Okay, so this allows us to control how much of the wave gets through. So maybe instead of half the wave, let's say we want 40% of the wave or something like that. And SCR gives us the ability to to do that. Okay. So if you look at the control wave half a rectifier, then the best way to think about it is we have a source in something like this, and then we will pick some time which will apply this gate pulse, right? Gate current pulse to SCR, so this SCR closes. And then the pulse we get is there's still nothing up until this point where we turn SCR on, and then it jumps to this point, follows a curve, turns off at this point, and this actually stays off, right? So until we apply the next pulse, right? So we could apply a periodic pulse, or we could just apply one and then this and then this, right? Okay, so it depends on how we apply this pulse. So most times we apply this thing periodically. So most times we apply this periodically. So this is Vs. So we apply it here, we apply it here, and we get a sort of some load voltage like this. Okay. So it's periodic output. This is called alpha, and this alpha is normally describing angles. Okay, so it's easier to talk about at what angle does it turn on, rather than if we talk about at what time, right? So it's easier to think of this as an angle going from 0, let's say, to 180, and we say something like this SCR turns on an angle 30 degrees. All right, so this is just a control halfway rectifier, right? Here. And then one thing we want to look at is now the average voltage across a load. Okay, so the average voltage across a load is basically, so let's say we have this dotted line, this is the source voltage, and then FSCR voltage basically is how much is this red part, right? So how much is this? Again, so think of alpha as a angle, so think of this as, let's turn on some angle, and then the average voltage is, which this thing still has a period 2 pi, right? So but instead of integrating from 0 to 2 pi, we're integrating from alpha to pi. This is only non-zero part. And then Vmax, let's say sine omega t dt. So say the source voltage is Vmax sine omega t. So I'll do this integral, and then so the short calculation to this will show that this is Vmax over 2 pi 1 plus cosine alpha. So this is a number that goes between right, so 1 plus cosine alpha is a number that goes between 2 and 0, right? So yeah. So depending on what this alpha is, you get a different average voltage, right? So there's a point of this y is controlled. There's this alpha parameter that is up to us to tune. Okay. And then we can compute the RMS voltage, right? So the RMS voltage, this is square root for 2 pi, integrating from alpha to pi, Vmax sine omega t, whole thing squared dt. And so this calculation sort of slightly more complex to do, but at the end of the day, the result is Vmax over 2 square root of 1 minus alpha over pi plus sine 2 alpha 2 pi. Okay? So this is something that you want to write down on your cheat sheet during the exam times. Right? But once we have the formula, then finding the average voltage is quite simple. It just you get all the numbers and then plug them in. So that's a half wave. And so half waves, the obvious drawback is sort of misses the negative part, right? So it's sort of not very efficient, misses half the wave. So we can, make a full wave rectifier out of the half wave rectifier. And the full wave rectifier now will require four diodes for us. So it's sort of set up in this particular fashion. And the idea is to offer a path where the current can go through, right? So offer a control path the current can go through. And we want to make sure that the current always goes in this direction. And so this applies, or current or the voltage is always in this direction. And so this is why we have this sort of particular dial setup, right? So this is four dials, the D1, D2, D3, D4. Okay, so let's see how this thing works. Why does this gives us a full wave rectifier instead of a half wave rectification? So the idea is basically, well, if the source voltage is positive, then we have this conduction from going from D1 all the way through across D2. So this is what happens when the voltage is positive. Then when the voltage is negative, our current now flows basically to D3 through this load and comes back through D4. So the output, the load always sees a positive voltage or positive current going from C to D, right? So basically what a full wave rectifier does is flips this negative part, right? So flips from negative to positive. Right? So we can trace this across, right? And so this is accomplished by using four diode instead of one, right? So the halfway rectifier misses half, and but only requires one diode. In this case, we can get the entire waveform, but now we're at the cost of requiring four diodes. We can do some calculation with all this. This is the average voltage of the full wave rectifier. It's 1 over 2 pi, 0 to 2 pi, Vmax. Okay, so be careful, right? So 0 to 2 pi, Vt, Dt. The thing to recognize is this is just a pattern repeated twice, right? So they're just green and red repeated twice. So the average is 2 times 1 over 2 pi if I just integrate one of these things, right? So if I just integrate the source, instead of integrating the source from 0 to 2 pi, 0 to 2 pi, we're now integrating the source from 0 to pi. And we just double this because we get this waveform twice, right? So this is 1 over pi, 0 to pi, Vmax sine omega t, d omega t. This is 2 Vmax over pi. And the RMS voltage across the load, we should recognize immediately, first off, is that uh, to RMS, this waveform and this waveform are equivalent because we're squaring this anyways. So it really doesn't matter whether this is, whether it's positive and negative or just two positive parts, right? We're going to square these. So we already have done this calculation actually. So this is VRMS is Vmax over square root of 2. Okay, so it's from before. This is the exact same calculation we did before. And again, the control for rectifier is just a full rate rectifier where instead of diodes, we use SCRs. So drawing this again, add all these ticks. And then now we have a control flow rectifier. So the idea is the same. Actually, so here I drew four SCRs. We actually only require two of them, right? Because, let me be clear, because we, we don't need two SCRs, it's sort of redundant. The two SCRs in a path. So we're going to just use sort of two SCRs and two diodes. And the way this works is if you look at this path, the blue path, S1, this SCR already controls when this path can conduct. So this D1 could stay a diode. Right? So we don't need D1 to be SCR. So we could have it as SCR, it's not necessary. And then the right path as well, we just need one of these things to be SCR. Here we choose this S2 to be SCR. And then we draw the waveform, this comes up. Again, basically this just flips. So it sort of has control at alpha, and then this is 0. This goes on again. So this is pi, and this point is pi plus alpha. Okay. So this is as before, is you would basically take the half-wave rectifier or controlled half-wave rectifier and just have this done twice. And the average low voltage is just 2 times what we had before, right? So before we compute the average low voltage for one piece, now I have two pieces. So it's just 2 times, right? So we average of the half wave control rectifier, and this is Vmax over pi now, 1 plus cosine alpha. Okay, so before we have Vmax over 2 pi, now we just have Vmax over pi. The RMS low voltage, again, we can compute this again. Right? So by doing some calculations on here, right? So again, the definition of this is Vmax squared over pi. So we want to think about this. This is just 2 times, right? Of this, right this way. So over pi sine omega t squared d omega t. So if you do all the calculation, this is Vmax square root 2 square root 1 minus alpha over pi plus sine 2 alpha over 2 pi. So this is the RMS voltage. And again, so to summarize everything, we can put things together. And we have average voltage, RMS voltage, and power. Okay, consumed. And this is a bunch of formulas for the control rectifiers. So we want the uncontrolled rectifier to set alpha equal to 0, right? So you don't need to write sort of two different formulas. If you want to, you can just write these formulas and by setting alpha equal to 0. And the power calculation, basically, this is just sort of VRMS squared over R. It's just the whole thing. Right, so this is right, so power calculation is fairly straightforward. So we can square this and do some simplifications, and we get the power formula here. Right, and the observation is the average voltage increased by a factor of 2. The RMS voltage increased by a factor of square root of 2 because we're doing the square root in the root mean square voltage. And then power increases by a factor of 2 again. So the square root of 2, because we're going to, the formula is VRMS squared over R, gives us that a full wave rectifier doubles the power of half-wave, as what you would expect. So this is our AC to DC rectifiers. Okay. So you may have a question, right? So, you may have a question of, well, a waveform like this really isn't all that DC, right? This is sort of always positive, but is this really DC, right? For DC, we typically think of something like this, right? This is what we think of DC. Okay? So how we make the circuit is actually after the rectifier block, we have this filtering elements. So we have this filter, and what this filter does is sort of smoothes out the waveform, so make it much more DC. But filter element analysis is a little bit, it's not that hard, but it is a bit involved. There's sort of a lot more equations. So for this class, we're going to ignore filtering. Okay, we're going to ignore filtering. We're going to think of just sort of in terms of average quantities. So certainly in the lab, you'll see some filtering, and in Pro 52, filtering is a huge part of power electronics design. But for this class, sort of we ignore the fact that you have to do filtering, right? So for this class, we just call this thing DC, okay? Even though nobody actually think of this as a DC waveform. Right? So now we're going to look at DC-DC converters, right? So DC-DC converters are there are two obvious things you can do for DC-DC. There is a step down. So think of this as some box. There's some V in, there's some V out, right? So step down means I want V out to be less than V in. This is called a buck converter, right? And I think in practice, this word is used much more often than step down converter. So people don't say we design a step down converter. They say we design a buck converter. And then the second thing is, obviously step up. This is called a boost converter, right? So we're stepping up the voltage. And then the interesting thing is we can think of as well, there is actually another type of DC to DC conversion we want to do. Okay? So it's not just step up and step down. Right? And the other thing we want to do, this is actually sometimes we want to reverse the polarity of the output. So what do I mean is this is, let's say I have an input, let's say 5 volts here. Okay, let's go into the device. Now I want, let's say this to be, say, minus 2 volts. So not only do I want to convert up or down, we want actually to change the positive and negative polarity of the voltage, right? So this could be useful if you think about, let's say we're plugging when you plug your charger into your phone, right? Nowadays, it doesn't matter which way you plug it in. So USB-C is it doesn't matter, you can plug in, right? So then what determines the right polarity gets into your phone, and there's a buck boost converter. So there's something that will reverse polarity if needed to. And so a lot of the older technology, if you look at all the cables, there's there's only one way you can plug in a cable. Right, so that's sort of fixed polarity. Okay, so, and this is, called a buck boost converter, right? So sort of run out of names here. So let's just say buck boost. All right, so buck boost will flip the sign and may do some voltage conversion after a fixed sign. Okay, so let's look at the buck converter. This is also called a chopper. So we'll see for obvious reasons. So this design of this is sort of really simple. It's just you have a switch. Okay, so we have some DC source, let's say VS, and we just put a switch in the middle of circuit. So if you want to know how this actually looks like, you can think of this as let's say bipolar transistor. And what the switch does is the switch is just on sometimes, off sometimes. So this is a periodic signal. Again, this is a periodic signal. This is time. This is sort of the switch action. So this is uh, this switch is on, this switch is off, this switch is on, and so on and so forth, right? And if you look at the sort of the uh, load voltage, this is just when the switch is on, we're at Vs. When the switch is off, we're at 0. When the switch is on, we're back to Vs again, and that's sort of really simple voltage output. And the average voltage is, extremely easy to calculate, 1 over tau. There's a T on. So recall tau, this is the period. There's a T on Vs dt, T on tau, Vs, and it's just a duty cycle times Vs, right? So the average output voltage, this is a number between 0 and 1. So some fraction of the output voltage. Okay, so let's look at an example of this. So let's look at some example. So let's say I have a buck converter. This operates at 5 kilohertz. So this is the switching frequency. You have an input voltage of 12 volts, average voltage of 5 volts. How long is, oh, yeah, we want to find T on. Okay, and this is sort of straightforward calculation. So the period, I just went over frequency, 0.2 milliseconds. We know that we average is equal to the duty cycle times the source voltage. So the duty cycle is 5 over 12, 0.417, and then T on just 0.147 times tau. This is 0.0834 milliseconds. Okay, so it's a very easy calculation to do. And then now we can compute the power, right? So let's say now I attach a power, attach a load to this. What is the low power we deliver? Okay. What is the RMS voltage and what is the low power we deliver? So in this case, we have the average current, right? Just the average voltage divided by the resistance, 5 over 10.5 amps. And we can compute the RMS voltage. We can compute the RMS voltage. This, again, by definition, 7.75 volts. And the interesting calculation now comes from the fact is, well, how should we compute the, right? So now we want to know is, how do we compute the power coming out of this circuit? So this is the interesting part is, what is that power, right? So basically, should power be the average squared over R or the RMS squared over R? Okay, so, and this is not an obvious question to answer. And the answer to this is actually a little bit ambiguous because our circuit is too simple. Right, so let's take a closer look at this. So this is a sort of somewhat subtle point. And the subtlety comes from the fact that right now for buck converter, we're thinking of the output voltage as something like this, right? So this is 0. But this is, again, that's, you recall the filtering discussion is this has Vs of, being 12, but there's an average voltage, right? What really happens for a circuit is we don't just have a switch here. Again, we have a filtering element in the circuit. And so the really how you should think about this is there will be a filtering element, and then the filter element will connect to the load. And what does this filter element do is if you look at the output voltage after we filter it, the output voltage will be sort of very close to the average voltage. Okay. So in this case, the power calculation is clear because the average voltage is sort of constant, just V average squared over R, right? But but if you look at this case, you tend to think of as P V RMS squared over R, right? So because right, we define for pure oxygenol, we should use RMS squared over R. So in this case, we'll pick up we'll say that we'll adopt this definition for power. As we think of the average power as the average voltage squared over R, because it's much easier to think of, to pretend there's a filtering element, and then this filtering element will get power to be the correct value, rather than to pretend that, we're looking at a pyroxenol, there's some power, then we're going to filter it, there's some different power, things like that, right? So to be consistent, we should just think of where the circuit is sort of magically filtered, and we just operate at the average voltage, right? So we adopt this definition. And this has a benefit of the P average is equal to V average times I average. So the power is voltage times current. So in this case, we will not adopt this. We'll take this one. This is 5 squared over 10, 2.5. And this is equal to V average. You can check I average. Okay. So from now on, our power definition for DC-DC circuits will take the average voltage. We'll look at the average voltage here. All right. So this is a buck converter. Now we're going to look at a boost converter. Okay. Now we're going to look at the boost converter. So a boost converter is a little bit more interesting. And the reason the boost converter is slightly more interesting is, well, how would you get the voltage to go up? Right? So the question is, well, I have some input voltage, I have some device, and this output voltage is higher than the input voltage. Okay? When you V out, it'll be greater than V in. And this is more tricky to do because we could not, just insert a switch in the middle, right? So in the buck case, we just insert a switch in the middle. Here, we really cannot do that. Okay? So the idea is, well, to step up the voltage, we need some memory element. We need sort of element with memory. Or this is sort of storage, right? So now we need to somehow store the voltage. So storage elements. Right, and this is basically just, we have two kind of elements that have storage, an inductor and a capacitor. So the question becomes, where do you put this inductor and capacitor, right? And the idea is to put the inductor and capacitor this way. So it's not, again, entirely trivial to come up with this circuit design. So here we're going to treat as given. And we're going to think of this bipolar junction transistor as our switch. So we have an inductor in front. We have a diode to make sure current flows the right way. We'll have a capacitor, and then we have a voltage output. And the idea is basically we can charge up to boost the voltage. Okay, so we'll sort of try to charge this thing to boost the voltage. And so with the idea is when this switch is closed, we're somehow sort of charging the voltage. When the switch is open, then we're sort of drawing this power out of this. Right? So to take a closer look is if we have when the switch is closed, we're basically drawing power from the capacitor. When switch is open, we're sort of charging the capacitor. Then the way to see this is that if the switch is closed, then the output circuit is actually not there because I create a short circuit through this. So that's all I'm doing is I'm just have this inductor. Again, I have some charging action on this inductor. And then if I have things open, then the source basically is present now. I have some inductor, a diode, a capacitor, and a voltage, right? So we're going to think of we're charging this capacitor and we're charging this inductor. And this is what makes the voltage appear higher on the output. And we'll do some calculation to see this. Okay, so not sure what happened on this slide. So basically, two cases, right? So first case we have is we have this. This is one of these, right? So this is Vs. And what we'll look at the current through the inductor, right? Our goal is to look at this current when the switch is on and when the switch is off. We want to look at how this current will change. It'll be useful to, right? So let's look at this current through it. Then useful to recall the equation Vs is L di dt plus Vt in this case. So so in the circuit as a switch is closed, we have Vs equals to L di dt. We're turning this around. Of I is basically 1 over L, the integral of Vs. And in this case, we have Vs equals to L di dt plus Vt, or L di dt equals to Vs minus Vt. So let's see what happened in this case. So first, when the switch is on, right, when the switch is closed, this tells us the current is just integral of the input voltage. Well, the input voltage is a constant, so the current has to go up like this, right? So this is what the current behaves like. As the current goes up, and in this, so this is come to T on. Well, now when I open the switch, I have this circuit on the right-hand side. And then this is the derivative of the current is proportional to Vs minus Vt. But recall that we want Vt to be larger than Vs. So this is negative. So this thing sort of discharges. Right? So this T off. And then charges again, discharges, and there's a periodic pattern that repeats. Right. So, and we assume that this is the circuit is in steady state. So what this means is there's sort of no net current buildup. Okay. So whatever current that we put into the inductor has to come out. Right. So this is the idea. Okay. Right. So and then we do sort of more calc. So the output voltage can be found basically through this current through this sort of current balance equation. Right? So if we look again, we look at the input current. Right? So something like this. This is current versus time. This is the inductor current. And then we can look at inductor voltage. This is the voltage of the inductor. And the voltage inductor basically is positive up until here, then drops to be negative, then positive again, then negative, and so on. So the way to think of this is sort of the energy into inductor, and this is the energy out of inductor. And so we have so they're basically the inductor is storing power, is storing some energy, and this is what sort of devices with memory does, right? So this is what storage devices do in our circuit. Right. So now let's do some calculations. Okay, so the calculation that we want to do is just a current balance, right? So if we look at how much current is charged versus how much current is discharged. And again, in steady state, they must be equal to each other, right? So that we want to apply this formula. Basically, this thing has to be equal to each other. Well, how do I find, how much current is charged? We have that Vs, in this case, is equal to L di dt, or the turn this around, I is integral of 1 over L Vs. And this is just linear proportional, so that's just Vs over L times how long you're charging. And this is Vs over L times T out. Okay. And in this case, we have Vt equals Vs minus L di dt. Right. So writing this way, we have di dt is Vs minus Vt over L. We're going to approximate this to be approximately constant. And we're going to think of this side as sort of approximately constant, and then I off again is just proportional to Vs minus Vt over L times how long this thing is off. Right? Okay, so now we have two equations, and we're going to simply equate these two. And so we have Vs over L times T on is equal to Vs minus Vt over L times T off. Some shuffling equations a little bit and solving for Vt, you have Vt equal to Vs 1 plus T on over T off. Okay. So this, this is Vs multiplied by a factor. This is greater or equal to 1. Yeah, sorry, so this is boosting up the voltage. And this boost action again just comes from the inductor and capacitor. It's mostly, I guess, in this case, inductors being charged up. All right, so then, what does the capacitor and the diode do? Right? So basically, the capacitor makes this approximately constant assumption, roughly correct, right? So what this does, this is sort of holds the voltage constant, right? So this is again a filtering element that tries to hold the voltage constant. And the diode is basically this diode prevents the capacitor discharging. So what this diode does is provide a capacitor discharge uh, to the inductor. And so we don't want the current to somehow come out of the capacitor going to the inductor. So to prevent that, we put a diode there. Okay, so we're gonna think of as, right, so for sort of large enough C and L, the output voltage is roughly constant. Okay, so we're gonna think of really, we have a constant voltage here instead of something that ripples. Right, and then for this type of circuit, you have power, then power is sort of obviously Vt times It, right? Yeah, equals to Vt squared over R. And in this circuit, actually, we have sort of no losses in the converter circuit, just inductor capacitor. So assuming these are ideal components, there's no losses, we have power in equals to power out. This is right, so we have power balance. So this is Vs times Is, Vt times It. So this is a very useful equation to use when you're being asked to compute the input current. So the average input current is most times more easily found by through this power balance equation rather than sort of direct current computation. Oh, we did. Right. So let's do a exercise. So let's say we have a boost converter that used to step up 20 volts, 50 volts, that's switching at 5 kilohertz, load is 10 ohms. We want to find the average current of the load, average power delivered by the source, average current of the source. And then the last question is sort of, how big the current ripple is. So let's do the first three, then we'll say more about that. Okay. So current and power is sort of, easy to compute, right? The output current is just Vt over R. This is 50 over 10, 5 amps. The power, again, the input power is equal to the output power, assuming no losses. Vt times It, 50 times 5, 250 watts. And then the input current is the input power over the source voltage, 250 over 20. Right. So these are the fairly easy equations. The ripple question is a little bit more interesting, and this gets to the fact that if you look at this equation, actually L, the value of inductance, doesn't show up. This sort of value of inductance sort of just completely gets canceled out in this equation, right? So right. So what does the value of L do then, right? So what the value of L does is sort of limits how big the current goes up and down, and we'll see it through this example. Right? So this is easier to do this in the example, right? So recall that we have is what does we mean by ripple? Ripple is basically if you look at the current through the inductor, it's something like this. And this sort of delta ion, or the same, delta ion is equal to delta I off. Right? So this is the ripple of the current. So current ripple is delta ion, or this is equal to delta I off. And the size of this ripple depends on the value of L, right? So this depends on the value of L, right? So different values, so larger the L, basically the smaller the ripples are. In this question, we're asked, what value of L will limit this ripple to 100 milliamps? Okay, so this is what we'll try to find. And if you recall, basically, what we have is we have that delta I on is just Vs over L times T on. Right? And we want this to be less than or equal to 100 milliamps. Right? So we want to solve for L. All right, so we know Vs. What we don't know is we don't know T on yet, but we can sort of figure that out. So we have Vt equal to Vs, 1 plus T on over T off. This is one equation we have. We have another equation that has as T on plus T off is equal to 1 over the frequency. Okay, so we have two equations now. We have T on over T off is equal to 50 over 20, and we'll have T on plus T off. This is equal to 1 over 5 kilohertz, 0.2 milliseconds. So these are two equations and two unknowns. This is actually a linear equation. Right? This is sort of a fairly simple linear equation in two unknowns. And we can easily solve this. We get T on is 0.12 milliseconds. And then our requirement is basically just Vs over L times 0.12 milliseconds, less than 100 milliamps. So for limit of 100 milliamps, I just have this as equality. Solving this gives L equals 24 millihenries. Okay. So let's stop this video recording here, and we'll continue with buck-boost converters next time when I return.